Okay, so this is what I remember. Let's say there's a graph like that, and then we have this a x is a variable, t y, this is f of t, right? Yeah. Okay, so this area over here is capital F of x, and then x is a variable. So the first fundamental theorem of calculus states that the derivative of the area is equal to f of x. So this is the area, so the derivative of the area, so how much the area is changing at this point, and that is equal to f of x. So let's say here this is dx, but dx is like infinitely small. I don't know if that's how you say it. So like it is smaller, infinitesimally small, I think. So how much the area changes for a very tiny increase in x, that is approximately equal to f of x. So first of all, the definition of this is that f of t dt, so the derivative of this is equal to limit, by the definition of the derivative, the area plus h minus f of x over h. Let's call this h, and then h is going to zero, closer and closer to 0, and this is equal to right. So I was here, so this we can expand. F of t dt plus x plus h, and then subtract it, basically this part. So basically what I'm doing, the area from a to x plus h is the area from a to x, and the area from x to h, x plus h, and then this and this cancel out, so we are left with or we can write this as, can write it like this. Now before I go any further, I just want to explain one thing. If I have a graph, areas a and b, let's draw, something like this. A, B. So the area over here, the area over here would be, let's call this G of T. The area over here would be A to B G of T dt. But no, not this. Suppose I have an average G of T, which is like over here. Yeah, I should draw a line. This is like G of C, C. So G of C is the average between G of A and G of B. So let me is average G of T on A to B. So this is the average. So the area of this hold on, is this is G of C B minus A, and the A, basically the average area over here, is equal to the area under the curve. Basically what I mean is this is equal to G of C B minus A, where G of C is like the average. So if I make G of C the subject, I can write it like this. This basically means G of C is equal to the area under the curve divided by the interval, which is B minus A. So now going back to our limit over here, notice from x to x plus h, and we are dividing it by h. So x to x plus h. So the area over here divided by h. And this will give the average f of t between x and x plus h. So this over here is equal to limit the average times it by h, which is the interval. Like, I hope you guys understand what I mean. Not times h, sorry. So the average value is the area divided by the interval. Same thing for f. The average value between these two is the area divided by the interval. And if h is going to 0, so if the area is smaller, so h is, hold on, so if the area is going closer and closer to 0, the average value of f would be equal to f of x. And that completes the proof, this proof. Now the second fundamental theorem of calculus is that per graph here I have a constant c. I have three constants c, and then the area under the graph is g of x. X is between, I think I should do it like this, between a and b. So g of x is the area g of x is basically the area over here. Area from c to wherever x is, and then x is the variable. So the second fundamental also I should also add that f of t, this over here is t. I should actually call it a of t is equal to this is the antiderivative of hold on, I made a mistake here. I should write the text. Antiderivative a of t is the antiderivative. If you take the antiderivative of a of t, you get f of t. So basically a of t if you derivate this, you get a of t. So the second fundamental theorem of calculus is that this area a b f of t dt is equal to the antiderivative at b minus the antiderivative at a. The antiderivative with the value of b and the antiderivative with the value of a. So like the derivative of x squared is 2x. The derivative of x squared plus 6 is also 2x. The derivative of x squared plus 7 is also 2x. Basically, derivative of x squared plus any constant c will always be 2x. So if you're taking the antiderivative, if you have 2x and you're taking the antiderivative, going to be x squared plus c, because we do not know this. Basically, another way of seeing this is if you have a graph, derivative tells you the tangent line. I don't know if this looks good. It's almost straight. I should do this again. Let's call it v. This is f v. So this derivative the derivative gives you the gradient. But if you knew the gradient, the formula for the gradient, you can get the shape of the original function back, but you cannot get the y-intercept. So the function could be this or this or this. So the constant, the y-intercept is unknown. So what I was saying is, yeah, going back to this, we know that the area, that this area in between is basically g of b minus g of a. And the antiderivative, like in terms of integral, the antiderivative basically means we know that the area, the endpoint of the area is b, but we don't know the starting point. So the starting point could be anywhere. The endpoint is over here. So a of b gives the area from an unknown starting point to b. Area antiderivative, this antiderivative at a gives the area to a, but the from is unknown. But if we are finding the area from a to b, we don't need the from part. So basically, even if the, let's say g of x was the area from here to x, g of b minus g of a would still give the area in between. If g of x is the area from c to x, g of b minus g of a would also give you the area in between. So if you have the antiderivative, this antiderivative would be like antiderivative at a particular point x would be this. I'm adding a c because we don't know the from point. The y-intercept is unknown. So if we expand this, the two c's cancel out. Plus c, and then plus c again, yeah. The two c's cancel out. And that gives us this, which we know is the area between a and b. So we don't have to know the original. We don't need this. lower bound, simply taking the antiderivative would work. And that is the second fundamental theorem of calculus.